I told you that Kuramoto-Shivashinsky equation describes the ring of fire, which is some periodic domain. Now, in your kitchen, the ring of fire has a discrete number of places where the gas enters typically. And you might find following kind of solutions. Maybe there are 7 notches on your thing, and you find some kind of flame, and you look at next 7 notches, and you find the same shape at the instant, and you look at next 7 notches, and same shape repeats itself. And as time goes by, they flip together. It's a mathematically possible solution of your CN. And what it means is that when I look at the group SON, so I have a group ON, which is O2 in this case, it contains a subgroup called SO2, but this one has lots of subgroups, and they're called cyclic groups, the ones that we know. So for example, this subgroup 2, subgroup 3, etc. And what it means is that these are states in which a solution is repeated discrete number of times around the ring. And they're totally legal solutions of your problem. And what happens typically when you solve your problem, you define them on some kind of domain. Now, if you double the domain, because you're trying to get a very large system, the solution that you had on this domain is solution of the bigger system, just repeated twice. So you'll find out that lots of problems, lots of things that you do have these solutions. Now this is bad because in this list there is also C27345. This is an endless list because every discrete subgroup is okay. And now the physics will intervene of the problem or chemistry of it. It'll actually select a finite number. And this is now physics, that's not mathematics. For finite size of the system L, you have a competition between instability and Laplacian that's trying to pump up things that are curved. And then there is a penalty, which is quartic penalty, that says if something is curved, I really bang it because I compute its curvature, square it twice, and it shows up in a sign in the equation in such a way that it decreases the solution when you check it. So that means that you won't be able in your flame, when you look at long time typical state, you won't see things that looks like hair comb that have 10,000 little things. They'll be smooth. So that picks out some finite number of sub-solutions. And in our applications where we look at small domains and try to understand dynamics of small rings, the first one that show up is the C2. But because this is group O2, there are states, there are solutions that have a symmetry which is called dihedral group 2, which is a group of 4 elements. 2 of them have to do. So C2 would be a group which is identity, and then you go around with the shift, which is, let's call it shift of translation operation 1/2, meaning I go 1/2 around the circle. So T1/2 is a rotation matrix, a representation of rotation matrix that in it has sines of pi and cosines of pi. So you rotate by half domains. Now D2 allows for a flip, so that has 4 elements. That's a group that has these rotations half around the disk, but it also allows for the flips. So let me call T equals T1/2. So there's also tau, and there is combined action of 2 of them. So it's a group with 4 elements. And now I'll put this in the notes because the group theory gets very tedious to keep writing on a blackboard, but I'll just tell you what the result is that now, because we have 4 elements, we'll have 4 projection operators. And I'll write these projection operators, and they're kind of sensible. And that means linearly therefore a reducible representation under that symmetry. You can write 4 kinds of functions. And because there are 4 elements, there is 1 4 showing up for normalization reasons here. And 1 element is always identity, so I'll write it as 1. In matrix representation, there'll be unit matrix. And then I insert these group elements that I have. And then I have flip followed by half translation, flip. And now you can check that these 4 are mutually orthogonal. So on the linear level, the decomposed space of all functions defined on the circle, this property that function does something and then half cycle later does it again. Or you can take any function and decompose it in 4 such functions that do it by these operations. And that now gives you linearly irreducible EREPs of what kind of functions you could have before you start evolving them. And ignoring that U squared term mixes them, the nonlinear term mixes them. There will be 4 kinds of things. There will be one solution is U. That's an equilibrium because when you stick it in this equation, that's always a solution. So that's the boring solution, 0 vector in this infinite dimensional space. But then you can define U plus space of functions to be the sum of projections on this projection operators 1 plus U3. Then there is something we call US, which is U1 plus U2 subspace, meaning obtained by these projections. And this is reflection irreducible of antisymmetric U of X. And this one is half-shift irreducible representations of symmetric solutions. If you remember, we had already decomposed the space in symmetric and antisymmetric before we started looking at the subgroups. And these guys are flow invariant. So this is a big deal. It means that this one is obvious, but these 2 subspaces, there are 2 subspaces that if I find a solution and I start in that subspace, let's say I find an equilibrium or something, then it'll stay in that subspace forever. And this one will stay in that subspace forever. So if I start finding more and more flow invariant subspaces as we start using more and more subgroups of O2. And I'll leave it at that. But the claim is that it's totally essential that you understand all the subgroups that are relevant for the size of your system before you embark upon mapping out the world of all possible solutions. Because having solutions of given symmetry really means something in a general problem. It will organize it in a very forceful way.